So today we're going to do Fermi liquid theory. That's the plan. So just to remind you where we left off yesterday. And so yesterday we left off at this point where we defined RS. We said RS was this dimensionless ratio of potential energy divided by kinetic energy, right? Which is A over A naught. A was interparticle spacing. A naught was the Bohr radius. So then we drew this phase diagram where RS is 0 is, what was RS is 0? Anyone? Was it, where was the free Fermi gas on this plot? 0, right? Yeah. So this is the free gas. And we pointed out that it was counterintuitive in that the free limit was where the interparticle spacing was much lesser than the Bohr radius. Then we said at really, really large values of RS, there is a crystal. And all the electrons just avoided one another and formed some kind of crystal like that. And today, and just to put yesterday's class in perspective, we said somewhere here is where our analysis could be okay. And today we want to talk about this intermediate regime where both the interactions and the kinetic term are equally important. And we want to develop a phenomenological theory to explain the experimental fact that the system here looks metallic. And that goes by the name of Landau Fermi liquid theory, because Lev Landau is the person who proposed it. Okay, so our prototypical system for this is liquid helium-3. So helium-3 has how many electrons? Protons? And neutrons? 1, right? Because I'm looking at the isotope. Just, seeing that you're awake. Okay, so 2 electrons, 2 protons, 1 neutron. So does that make this a fermion or a boson? A fermion. Okay, so that's good. At least we have a system with fermions, because we were going to describe a Fermi liquid. In its phase diagram, this is pressure, that's temperature. This is here there's, at low temperatures, they're more interesting superfluid phases. But for our purposes today, somewhere between, this is in millipascal. We want to describe this phase called the normal liquid, which is in somewhere between 100 millikelvin and around 0.1 millikelvin. Okay, so it's not the gaseous phase of helium, it's the liquid phase, and it's at pressures of 1 to 2 millipascal. It's somewhere between 0.1 millikelvin and 100 millikelvin. So in here, it turns out that this RS parameter that we defined is roughly 1. Okay, so the interparticle spacing between the helium-3 ions is about an angstrom. So when I plug this into my formula that I wrote down yesterday for T Fermi, right? T Fermi was related to the Fermi energy over Kb, related to Kf square h bar square over 2m, and Kf was the Fermi vector, we said, okay, it's about 2 pi. It's a wave vector, so it's 2 pi over length. The length scale is interparticle spacing. So if I plug this in here, I have something which is square h bar square over 2m. Okay, great. Plugging in numbers. In here, in the normal liquid phase, I find TF is about 300 Kelvin. Okay, so that's good. This fits our criterion that we said yesterday. We would like this Fermi temperature to be much, much bigger than than the temperature at which we want to describe the physics, which is in millikelvin. Okay, so we have a huge separation of scale there. That's good. Can anyone guess what TF is going to be at room temperature? Where if I'll give you one piece of information. Interparticle spacing, instead of being an angstrom, is now a nanometer. What's that? Is that the way it goes? If A increases, TF decreases. So it's about 3 Kelvin, yeah. Okay, so at room temperature, we don't worry about helium being a fermion, helium-3 being a fermion, because room temperature is like 300 Kelvin. T Fermi is 3 Kelvin. It's a classical gas. Okay, so this is not where we're going to talk about using Fermi liquid theory. It's at much lower temperatures where this is TF. Okay. So what is Landau Fermi liquid theory? What is the first assumption, I guess? So this is this, if you wish, the starting point, starting assumption of how we want to start describing liquid helium-3, okay? So starting assumption says that the low energy eigenstates for the interacting problem, so with interactions, is in one-to-one correspondence with the low energy eigenstates without interactions. Okay? So this is a huge assumption. Okay? What are we saying here? We're saying we know we solved the problem yesterday for the Fermi gas, so the helium-3, if you wish, at very high temperatures without interactions. We knew what all the low energy eigenstates were. In particular, we knew what the ground state was, which is, I use GS to represent the ground state. And we knew what the excitations were. We discussed them yesterday. And now we start with this very non-trivial assumption that there is a one-to-one mapping from these eigenstates that we found here to the actual eigenstates in the presence of strong interactions. Okay?
How can we justify or motivate this assumption? Can you just plug that in the head?
So I think the most compelling way to see this, I'm not going to show it to you, but the most compelling way to see is to do an RG analysis of the problem with interactions. And you see that it flows, the fixed point flows to a problem without interactions with renormalized parameters. So that's the sharpest way to actually make this connection stick. This is not the way Landau did it. He kind of said it. A phenomenological theory came out, and then you can microscopically try to do perturbation theory and connect it. But that's not rigorous. The best way to say it is if you did RG, the renormalization group, you would find that the fixed point is this. Okay? But I'm not going to.
Okay, we're assuming that we're close to or at some sort of critical.
So the Fermi gas is a fixed point in the sense that, right, because we discussed that this was the ground state, which is the Fermi surface, and we had this huge number of low energy excitations about the Fermi surface, which was, particle hole excitations like this. So it's a critical theory in the sense that there's a huge number of low energy excitations, right? So I can just, any fixed point, when you say critical theory, what you want is you want some low energy theory, and with an infinitesimal amount of energy, you should be able to create an excitation. And that's certainly true for our Fermi gas. Okay, so this is our assumption. Okay, I'm not going to prove it, but let's see where this is going to take us. Okay, so what this means is that I can label these eigenstates by, I put these in quotation marks because they're not the same occupation numbers in the non-interacting setting, but there's something like them. So there's one-to-one correspondence between these eigenstates, and those eigenstates tell me that there are some quote-unquote occupation numbers, which are related to the actual occupation numbers that we discussed here yesterday. So let me call this tilde. This is this operator here, and we knew that in eigenstates this was either 0 or 1, and so there's some related operator here, which is either 0 and 1, and labels all the eigenstates with interactions. Okay. Further, as we turn off interactions, the eigenstates here are smoothly connected to those here. Okay, this is, in particular, there are no phase transitions, no symmetry breaking, nothing. So let me give you a familiar example in, d is equal to 0 quantum mechanics, like particle in a well, for what I mean by this. So the statement here is that as I turn off interaction, so I'm here, there's a parameter u, say that controls the interaction strength, and so here the u is some u naught, here u is 0. And as I slowly tune these interactions off, the claim is there are no phase transitions, there's no symmetry breaking, and I can smoothly follow every single eigenstate from here to there. Okay, so let me give an example. What do I mean by smoothly follow eigenstates? So let's think about a system that we understand really well. So a square well, which we've all solved, long time ago. So I'm thinking about square well potential. Initially, let me think of infinite depth and finite width. Right? Okay, so this is the picture of the potential. V of x versus x. We know the solution to this problem. We know that the eigenstates look like, right? They have this form, and the energy of the nth eigenstate is, I don't know, it's proportional to n square over a squared. A is this width. Okay, so this is just a solution to the particle in a well problem. Now imagine I slowly increase the width a. Okay, so same particle in a well, infinite depth, width is increasing slowly. Well, at each value of a, you can solve the problem exactly. And what you find is that the nature of the eigenstates don't change. You still have an eigenstate that looks like this, one that looks like that. Their spacing has reduced, but their values of the energies are still at, if this is A prime, energy is still n squared over a prime square. Okay, so this is an example of a case where I can follow every single eigenstate. I just pick the value of n of interest, say this one, and as you increase the width of the well, I know this wave function is going to stretch out. Its energy is going to change like this, but I can follow every single eigenstate, no problem, right? And they all remain bound states in the well. Contrast this to the particle in the finite well. So now I think of finite depth and finite width. Okay, so here are the states. This is my finite well. Now, because I have a finite depth, well, this is actually infinite. Now I have finite depth. You know that an eigenstate in here is going to look something like this, but it can leak out a little bit. Right, so this is a bound state. It's got energy. Let's say this energy is 0. This is negative v. It's got some negative energy, so it's a bound state. It's mostly stuck in the well, but it can leak out a little bit because of quantum mechanics allows you to tunnel through barriers. So that's this. Now, again, imagine the same experiment, right? I'm increasing the width of the well. You see that I can follow some of the states. However, if this state actually, no, sorry. Let me decrease the depth so it makes it even clearer. I'm decreasing the depth of the well now instead of the width. And you see that as I decrease the depth, some of the states, instead of looking like this, are going to vanish into the continuum where they look like this. Right? So we know the particle in the finite well has two kinds of states, bound states like the one I drew here, and states in the continuum up there. And as you change the depth of the well, for some of the states, their nature could change from being bound to becoming extended. Okay, so in this case, I say I don't know how to follow the eigenstates. The nature of the eigenstates themselves have changed. When they vanish into the continuum, there's a continuum number of them as labeled by their momenta k. And they're no longer labeled by this discrete label n there. And so in this case, I say I cannot follow the states. So this statement here is somehow the first scenario, not the second. Okay? And just this second example, I don't know if that is more familiar, is yeah.
But in a similar sense to what you did up there, if you kept on increasing the width, you would end up with all the states fitting it inside. But I mean, there you were increasing the width. Now you were changing the depth.
Right.
So how are the two in some sense equivalent? I mean, you're comparing depth with width.
No, I'm just trying to give you two different ways to change parameters in a Hamiltonian. Okay. In one, I was changing the width, which is some parameter in Hamiltonian, and trying to argue to you that I can follow eigenstates because somehow the number of states in the spectrum hasn't changed, the labels haven't changed, and their nature hasn't changed. All that's happened is that, oh, instead of being slightly narrower, it's become slightly broader. The second kind of experiment, I'm not trying to say they're the same. In fact, I want to say they're different. Second kind of experiment was to change the depth. And there, if a bound state remains a bound state, okay, good for you, you can still follow it. However, some bound states are going to escape into the continuum as you decrease the depth, and those I cannot follow. That's the same. Yeah?
You say that here the width is a parameter of the Hamiltonian. It's actually a parameter of the boundary conditions that I have.
Well, so think of a specification of a problem in quantum mechanics is Hamiltonian plus boundary conditions. So
in this case, when you have the interaction, what you're going to kind of tune is the strength of the
interaction, yeah.
Right? Yeah. So in that sense, that's equivalent of you're changing the boundary conditions of my system. Or you will consider just a system with the same boundary conditions that you tune the parameter of the Hamiltonian.
So I can, this thing which you think is a change in boundary condition, I can rewrite it as a change in the Hamiltonian as long as, right, actually the potential in the Hamiltonian looks like V of x is some u naught times some, right, theta function minus some other theta function. So, I mean, I can take it at, I can write it as in the limit of really large depth. This is a change in the actual potential, right? And so this is always true in general. Something that looks like the change in boundary conditions can be made to look like a change in the Hamiltonian. Yeah. And in fact, if you wish, I haven't changed boundary conditions here in that I require it to always vanish at the edges of the wall. That hasn't changed, right? Just the points for it. Okay. A second example, and it's maybe it's useful to think of when you do your tutorial today. Today, when you're going to do a Hartree-Fock calculation following what we did yesterday, and what you're going to find today is that, so this U, that U for me controlled interaction strength, as a function of U today in Hartree-Fock, you're going to find that there is a transition from the metallic state where the magnetization is 0 to a ferromagnetic state where the magnetization is not 0. Right? This is called Stoner ferromagnetism, I said yesterday too. So basically what you'll find today when you do Hartree-Fock is that because of the Fock term that we discussed yesterday, the spins tend to want to align. The Fock term likes the spins to align. Once the interaction is strong enough, the state where the spins are all aligned is favored more than the state where you have both kinds of spins in the Fermi surface, and then the state has a non-zero magnetization. So, and I bring this up because I want to tell you that Landau tells you when you tune interactions, you should not go through a point like this. Right, so here too, you see that the nature of the ground state is changing. One, it has fully aligned spins, and if you wish, there are degenerate states here where all the spins are aligned, say this way, or the spins are aligned this way. You know, there's lots and lots of states. These are all perfectly good ground states. Whereas on this side, there's a unique ground state, which is fill the Fermi surface with equal numbers of up and down. Right, so going from here to there, there's lots of degenerate ground states. Here, there's just one. How do you follow it? You can't. So Landau tells you this kind of thing should also not happen when you turn off the interaction. Okay, so let's state the assumption there in somewhat more mathematical terms. So consider the state in the non-interacting gas obtained by adding a particle with momentum p above the Fermi surface. So we can rewrite this state as Cp, say we put the spin up, so Cp up dagger acting on sigma, so sigma, not sigma, whatever, omega. This here is my ground state. And the ground state always for me is not, it's not the vacuum that you're used to in field theory, in that my vacuum or ground state always has particles filled up to the Fermi surface. Okay, so there's always particles filled up to mod kf, and that's this state, and I always create excitations over and above that state. Okay, so in this state, the occupation numbers are, as usual, 1 in the Fermi surface. By construction, this is set to be 1. Everybody else is 0. And now Landau tells us, take this non-interacting state, turn on interaction slowly. Okay, so turn on it, just to be explicit, the interaction term that we dealt with yesterday looked like this. Right? That was the term we were done yesterday. And so we imagine tuning, I don't know, let's put a parameter up front, if you wish. Some parameter u up front that controls the overall strength of these. Yeah?
So yesterday we said that the expectations that I have from the Fermi surface have to come in a pair of particle holes, right?
Yeah.
Or the number. So you're assuming here that the number of particles is also conserved when you turn on the interactions, or not? Or not at all?
So there's different kinds of excitations. One, as you say, if I conserve total number, they have to come in particle hole pairs. Like I have to destroy a particle here, create there. However, if I allow, there are also excitations in which there's just one more particle in the system that looks like this. Right? So, yeah, when I turn on interactions, I want to follow all of them. All the states with in the sector with n electrons, the states in the sector with n plus 1 electrons, and this is a state with n plus 1.
So where the case where you don't have a particle hole there, how does the extra particle come in? Where does it?
Where you mean? Where? So it's in if instead of, I can just work in different number sectors, right? So the ground state, say, has n fermions. I can just imagine there's an experiment in which I put in a particle. So in tunneling experiments, it's called this, right? That's literally what they do. They take a tip to the sample and they try to inject electrons into the system. So imagine this is something like that. I can definitely experimentally, I can try to put in a current into the system and change the number of fermions in the system. It's not, there's nothing sacred about it. And I'm not changing the density. I'm literally, n here, like we said yesterday, is 10 to the 22 per centimeter cube, right? It's a lot. And I'm asking about what's one more fermion, what's two more fermions above it. So, yeah.
So then your omega that you have there belongs to the Fock space of what, n or n plus 1?
Omega belongs to the Fock space of n.
But then,
So then one more particle, this belongs to the Fock space of n plus 1. Okay. Okay. Okay, so two important points about this interaction. First, like we said yesterday, notice that it conserves the total momentum, right? So it destroys two particles, creates two more, but it does it such that the total momentum change is 0, right? So if whatever the starting momentum of the state was, this interaction cannot change it. That's one. Two is it also cannot change the total spin of the starting state, right? So does everyone see this? What this interaction cannot modify is the total momentum of this starting state, which because I have a filled Fermi surface with just one particle momentum p, the total momentum k vector of this state is p, right? Because the ground state has 0 momentum, because for every filled state with momentum plus k, I have one with minus k, right? So that the total momentum of the ground state is 0. If I put a particle with some particular momentum on top of it, this is the momentum of total state. So statement number 1, interactions cannot change this total momentum. So whatever I end up with on the other side, better have total momentum k is p vector. Okay. Second analogous statement is that the interactions cannot change the total spin. So the ground state has an equal number of spins up and spin down. So it's the total spin in the ground state it's in the singlet, it's spin 0. When I create a particle with spin up there, ground state has spin half. This particle excitation has total spin half. Again, interactions cannot change this, so I better end up with a state with total spin half. Okay? So these are the most general things you can say with just looking at the form of this interaction. We still don't know what the state looks like here. So suppose we looked we asked when we do perturbation theory on this wave function because of this interaction, what kind of excitations do we build in, right? So I can just do first order perturbation theory where I say psi 0 plus right? This is just perturbation theory. N here labels all the states except the ground state. Well, you know what I mean, except N not ground state. And so let's get a sense for if we could do perturbation theory, what kinds of states will, what would be the kinds of excitations that would be mixed onto this state when we turn on interactions. Right? Do those words make sense? So mixing or dressing, this idea is basically to say that here you start with a state which looks like just one particle above the Fermi surface. What this interaction does is it basically creates particle-hole pairs above this that preserve the total momentum. Okay, so I'll give you an example. One particular state that can come in through perturbation theory is one in which this particle is scattered here, and this to compensate for the momentum increase and energy increase, just to compensate for the momentum increase, there is a hole that's scattered here. Okay? So the state that I have left has now two particles and one hole. So I started with this state, which has one particle. When I do perturbation theory and try to compute the first order correction to this wave function, I found that I had terms in here that would involve two particles and one hole. Okay? And then if I went to higher orders, I would get more and more number of particle-hole excitations, and they always come in pairs. Okay, so that's what, if I did perturbation theory, and I tried to write down what this wave function will be, that's what it will look like. It'll look like this, dressed with particle-hole excitations, right? So what Landau tells you is that this psi p up, this wave function, once you turn on interactions, so let me call this and here I put a tilde to say that it's with interactions, actually looks like this. Okay, the tildes here refer to interacting, no tildes non-interacting. So the ground state has changed. I put a tilde on it. It's no longer what it was before. And psi tilde p up is what's adiabatically, what's connected to this when I turn off the interaction. And what Landau tells you is that this is, can be thought of as being created from the ground state by acting on with the creation operator, which is a new creation operator called Q. Okay? So far, I've not told you anything. I'm just kind of writing down what that assumption that we started with would mean in terms of creation and annihilation operators. So I've not told you how Q is related to C's. I've not told you how this is related to the original ground state, right?
Are you saying Q creates a particle pair? Is a creation operator for a particle pair?
Q is a complicated operator that creates a particle, particle plus particle pair, particle plus two particle hole pairs, everything, right? So just imagine this complicated wave function, and it creates that whole mess. That's what Q is. Okay, so this here is Landau's quasi-particle. A few more things that followed from the general form of the interaction. First, these quasi-particles, which are these complicated objects involving multiple particle Hall pairs and particles. First of all, they obey Pauli's exclusion statistics themselves. Okay, that is, they behave like fermions, and because we started with a state where p vector had to necessarily be, for this state to be an allowed state, it had better be true that the momentum be above the Fermi wave vector. And so we end up with a state as well, because the total momentum cannot change, in which the total momentum is above the Fermi surface, right? And so, however, if we had started with a state where the momentum was below the Fermi surface, there would be no state allowed, and there's no state allowed here as well. So Pauli's exclusion principle, because the total momentum is conserved, actually whatever you would have said for the bare particle excitations here follows for these more complicated Q objects here. So they themselves obey Pauli exclusion statistics. Okay, and this restriction has to hold true.
Can you repeat that argument, please?
About the Pauli exclusion? Okay, so so first let's start with this state where we know we had this restriction by Pauli exclusion. On turning on the interactions, because the total momentum cannot change, I know that on this side as well I have the same restriction.
What justifies that the Fermi momentum is the same with the interaction theory as the free theory?
So I'm trying to justify that to you. This tells you that so I start with a state where here you have no problems in saying that the momentum had to be bigger than kf, right? Otherwise, this state is just zero. This would annihilate the ground state. Now I turn on interactions. I get something complicated. However, I know its total momentum is the same as what it was before, which by that inequality there has to be bigger than kf itself, right? So the only states that I can follow from here to there are with p greater than kf, and they end up at states with p greater than kf, right? So you see that kf gets its meaning here because it had that meaning. It's coming from here, and the fact that the momentum is not changed by the interactions. Okay. Any other questions? So these are the most general things. Just to summarize, the most general things you can say about the Landau quasi-particle: it's a fermion, it obeys Pauli exclusion statistics. The Fermi wave vector, as you said, is the same before and after interactions. Yes?
I understand the momentum is the same before and after. How is that telling me that it obeys Pauli exclusion?
Well, okay, not quite. So the momentum being same before and after tells you that this is true, right? Now imagine writing down the entire family of states that you can follow at different p and different spin, right? You will follow them to the same states which obey the same, yeah.
But
So,
in some sense, you have to include the statistics, spin statistics to justify the fermionic nature of the quasi-particle. I mean, does this argument not work just as well? So what I'm saying is, can you point out what the flaw would be in the argument if I instead said that the quasi-particles were bosons? Where does it fall apart?
well,
Because it just works just as well for bosons, apparently.
well, not quite, because think this side already would fail. If I had bosons, there's no Fermi surface, and it's not true that I have this kind of a restriction on my non-interacting thing. So if you wish, all I'm trying to argue to you is that it inherits the features of the non-interacting problem, right? And the bosonic problem for the non-interacting problem does not have a Fermi surface. Instead, you should be thinking about condensed states where all the bosons sit at k is equal to 0, for example. And
That's when you're at 0 temperature. Like, so what if you were in some sort of
even then, there is no, so this is a fundamental difference between bosons and fermions. There is no Fermi surface for bosons, because even at finite temperature, because there's just no exclusion principle, right? And the distribution function that we wrote down yesterday, right, it does not look like this. 1 and 0 was, instead, right, nk sigma is not bounded above by 1. It can be pretty big. And so this looks completely different. There's no notion of a Fermi surface. So it's not.
That's the only natural way to go back to that.
Yeah, I'm not claiming this is true for bosons. And it was important to me that there was a Fermi surface for my non-interacting particle. Yeah.
I understand what you say when this condition of P greater than the Fermi level of the free theory means. But it might happen that the interactions can lower the Fermi surface, right? So that there is a hole between the interacting Fermi surface and the free Fermi surface.
Then there would be a contradiction, because there would exist states here that I could create particle-like excitations with P less than Kf, which are not adiabatically there. So the adiabatic, I'm using the fact that I can follow every single eigenstate here to there. So if there existed some new ones here because of the Fermi surface became smaller somehow in the interacting problem, then there would be new particle-like excitations at momentum less than the original Kf. And those I cannot follow back because they don't exist here.
So let me see if I got this right. So if I want the states to be adiabatically connected to each other, it somehow justifies that in the interacting theory I can define a Fermi surface that is the same Fermi surface of the free theory.
The same, at least the same
Oh, at the same
Kf. Yeah, yeah. But you understand, right? If it was different, so let it be Kf bar, then there exists, which is less than Kf. Then there exists momenta which are between Kf bar and Kf, for which I can write down particle excitations here, but have no analog here. And that's why I have the same. Okay. Okay, so good. So we have some sense for the Landau quasi-particle. Analogously, we can go through and define the quasi-hole. Right? Same idea, only it's a destruction operator here at a momentum below the Fermi surface. Absolutely same idea otherwise. Okay, so this defines for us the quasi-particle and the quasi-hole in the interacting theory. Here. Okay, so let's now talk about the relationship between the Q objects that we've introduced there and our original non-interacting hole and particle excitations. Okay, so I want to talk about two things. One is that somehow for this adiabatic continuity here to be true, right? At least at really low energies, so that this momentum P is very close to the Fermi surface. It can't be that the excitations are too different. Somehow if this excitation looks very, very different from this one, it seems hard to believe, even based on the kind of particle in a well analogy, to see how you can follow it. Okay, so let me make that sharper. What do I mean by looks too different? So it turns out that this state that we defined as the eigenstate of the interacting problem so this is the eigenstate of the interacting problem, and we define Z to be the overlap between so take the state created from, take the interacting ground state and use your original non-interacting electronic operator, the one that created particle excitations in the non-interacting problem, this guy, right? and use it to create some state in the interacting problem. The statement is that this state has non-zero overlap with the true eigenstate, which is created with the true quasi-particle operator. Okay, I'll repeat this slightly slowly again. So this thing here is this, which is the true eigenstate of the non-interacting problem. Okay, this is the actual single particle, one particle excitation in the one particle excitation in the interacting problem. This is interacting eigenstate. What this relation is telling us is that the state created by the bare electronic operator, the non-interacting C, has a non-zero overlap with the true eigenstate created with the interacting Q. The Z is greater than 0 in the thermodynamic limit. Okay, so
isn't that just a restatement of the fact that you can perturbatively construct Q from C?
no, give me 1 second. It's not at all trivial. Let me just orient you as to why this is not a trivial statement. First is, without any interactions, obviously Z is 1. Okay, so without any interactions, Q is the same as C, and this is obviously 1. Okay, 2, our claim here is with interactions, so this is without interactions. With interactions, it turns out that Z is less than 1, but it's still bigger than 0. Okay, and why is this non-trivial at all? Maybe this is just obvious, always happens. So let me give you a general argument for why overlaps like these between different states in a many-body Hilbert space is usually exponentially small in the volume, as opposed to a number. Okay, so imagine that we have, let's go back to our example of ferromagnetic states. So I imagine that I have a lattice system with spins on them, and this is my lattice of spins, and they're all completely aligned with one another. This is what I mean by ferromagnetic state. So this, for example, is a perfectly good guess for the actual ground state wave function, okay? Which is the ground state wave function is a product over all sites, spin up on each side. Okay? Now, a perfectly good ground state, which is also ferromagnetic, is one in which all the spins are tilted just slightly this way, but still completely aligned. Okay? This is also perfectly good ground state. If you wish, it's just like redefining your axes a bit. However, when I write down the ground state here, I find that, say it's, I add in a little epsilon of down, then by normalization I have okay? So this is my new ground state. Again, it's just a product of this wave function on every side. Let me call this sigma 1, omega 1 and omega 0. However, if you now look at the overlap, you see that for each site, you pick up square root 1 minus epsilon square, power number of sites, right? And if you rewrote this, this is just e to the minus n. And there's some logs and stuff. And the limit epsilon is much, much less than 1. It's going to look like this. Okay, so again, what was the point of this exercise? The point of this exercise is to show you that usually if you looked at two perfectly reasonable states in Hilbert space, both of which you think should approximate a ground state in a physical system, the overlap is generically supposed to be, will be exponentially small in the size of the system. Okay? And I mean, if these wave functions are random, that's even more easy to see. So all I'm telling you is that there is a one vector. The Hilbert space has 2 to the n elements. N is my number of sites. I have a spin 1/2 on each side, so I have 2 to the n Hilbert space elements. And if I pick two vectors in this Hilbert space at random, their overlap is generically going to be exponentially small. Right? And I tried to give you an example, which is even for physically motivated ground states can have exponentially small overlap. So I say this because the fact that a state created by the bare electronic operator, which is somehow approximate, versus the true eigenstate, the fact that it has a non-zero overlap in the thermodynamic limit, it's a very non-trivial statement. Usually, this is expected to be exponentially small in the size of the system. And for example, I know if I looked at the overlap between the interacting ground state and the non-interacting ground state, this is, for example, exponentially small in the volume of the system. However, if I look at the single particle excitation about the interacting ground state created by the C or by the Q, the overlap is non-zero. Okay, so yeah, any questions? Yeah.
So when you consider this two possible ground state for the ferromagnetic state, you're not saying anything about the interaction that you have, right? I mean, I'm thinking that we're going into the regime where the potential energy and kinetic energy are almost same, right?
Yeah.
But if you have, for example, in this example, it seems like the interaction is kind of small, right? If you're considering epsilon small.
No. So this is not about interaction. This was just saying that candidate ground states for, and these are these both will give you the same energy, because the energy is only, are the spins aligned with one another? And yeah, they're completely aligned here and they're completely aligned there. So these two are perfectly good ground states, which will give you the same energy for a Hamiltonian, which just has like some kind of S dot S interaction. Okay? What I want to tell you is that generically, though, even though they're perfectly good ground states will give you the same properties, their overlap is exponentially small, right? And that's just because these are big vectors in like a huge Hilbert space, and even if you make a tiny error in each site, which is like this, the error multiplies and you get an exponentially small overlap. Yeah.
So does this second statement about this Z being non-zero, does it follow from the other assumptions, or is that something that the fact that this overlap is
No, I think it's a separate. Yeah, it's a separate statement. Yeah.
Do the spin and momentum indices in Z have to be the same? Like you have K alpha and K alpha.
Yeah.
Like is it not? It's just the sum of the components. Because the way I'm thinking about it is like your new excitation is some sum of the like old particle excitations.
Right, but it always has to have the same total momentum and same spin.
Right, but like the individual spins don't have to be the same.
The individual spins, no, so all the spins in you mean the particle hole excitations that you create on top, right? No, they don't all need to have the same spin. But think of this index here is representing the total spin, and this is the total momentum. And this operator acting on top of this state also creates a state with the same total spin and same total momentum. So, or maybe more specifically, if I pick these to be different, I should expect the overlap to be 0 because they will just be states at different momentum or different total spin. Does that make sense? So I need them to be the same. And indeed, in writing this state out, I will have lots of particle hole excitations with other momenta and other spins. It's just the total has to be K, and the total spin has to be alpha. Okay. Right. So I want to get through at least one more calculation that maybe is the, what do I want? the first consistency check on this picture, right? So far we've just been stating things and just basically asserting them. So let's do one of the simplest calculations to check. It's not proving, it's just consistency check on this picture. And so what we want to do is estimate the lifetime of a particle excitation. By Fermi's golden rule. Okay, so basically what we want to check here is that in the non-interacting case, we imagined that this was the Fermi surface, complete filled states. We had a particle here at momentum p. And we already said that even at first order in perturbation theory, the interaction, H int, causes a process which scatters this particle to a different particle here while exciting a hole. So actually I'm changing. Let me call this K minus Q. Okay? So this involves taking the particle here, moving it there, while exciting a hole from inside the Fermi surface to outside. And clearly this process conserves momentum, right? As the way I've drawn it, the way I've picked the momenta, it conserves total momentum. So we already know that this is a process even at first order in perturbation theory because of the interaction. And clearly this will cause a decay of this single particle excitation, because if there is a matrix element for this process to happen, then you might at t is equal 0, you might create the excitation, a particle excitation at this momentum here, but you know that over time it's going to decay into a particle and a particle hole excitation here. So there's a decay rate for creating a particle here. And Fermi's golden rule is exactly what you use to estimate what the decay rate of this excitation is, right? And so what do we want to find before we go on the calculation? What we want to find is that this decay rate is very small. We want to somehow show that this particle is a long-lived excitation despite interactions. If I move very close to the Fermi surface, its lifetime goes up a fair bit so that I can define the particle is an excitation that I can talk about despite interactions, and then hopefully, therefore, I can also talk about quasi-particles. Okay, so does everyone understand the aim of what we're trying to do? If our excitations themselves are not well-defined, how can we talk about following them adiabatically and defining quasi-particles? Okay, so we're just doing consistency check that excitations are well-defined even with interactions. So let me state the result, and then we'll kind of geometrically derive it. So let delta E be the energy of this particle excitation above the Fermi surface. So delta E is h bar square over 2n k square minus kf square. And say that I define k vector relative to the Fermi wave vectors, just to simplify this. Then if this is very small compared to that, then this is approximately okay. So all I'm doing is expanding the energy near the Fermi surface, and I find that it depends linearly on the difference between k and kf. Okay, and so what we're going to show is that through Fermi's golden rule, the lifetime of this excitation, tau, tau k scales as delta e to the power minus 2. Okay, so just sanity checks. What this is telling you is that in the limit that delta E goes to 0, that is that this particle excitation is very close to the Fermi surface, the lifetime is diverging. So that's good. We've gotten a result that, as we set out to show, is one that tells you that the excitations near this Fermi surface are very, very long-lived. In fact, this is how long-lived they are. Okay, so this is what we're going to derive. And this is going to be a consistency check on Landau's Fermi liquid theory to the extent that we can say excitations are at least well-defined at really low energies near the Fermi surface. Okay. Yeah. One of you.
No, I don't know. This is just very naively treating this. Delta E is sort of some uncertainty. Is this, in some sense, an uncertainty in energy which leads to a similar uncertainty lifetime?
No. It's the difference in energy. It's the energy of the excitation that I create, right? So it's how much energy I put into the system when I created this excitation. And it's not an uncertainty. Imagine that I'm doing this calculation at 0 temperature, which is actually where I am. So there's no fuzziness to the Fermi surface, nothing. All I'm trying to estimate is, for an excitation with this much energy above the Fermi surface, what is the lifetime? And this is my answer. It's not energy time is h bar, nothing like that. Yeah? Okay. Okay. So there's a nice geometric way to do this. So first, let me write down what Fermi's golden rule is. Fermi's golden rule tells you what the rate of decay is. So the rate is the inverse of the lifetime, h bar over the inverse lifetime. And so it's 2 pi q(k) prime. Okay, so let me just explain this notation. Can everyone see this, or does this look very... No. Oh. Okay, I'll just write it below bigger, okay? I can't even say what we're... Oh, okay. K square. Okay, just let me explain this a little bit. H int was my interaction term in the Hamiltonian. This state K here was the, well, let me just write it. It's CK, oh, sorry, I'm suppressing the spin index for this part, just because. Okay, so this is CK dagger acting on the ground state. That's this state, the particle state excitation that we've been talking about. This state here corresponds to a particle at k minus q, a particle at k prime plus q, and a hole at k prime. Okay? So I'm asking for the matrix element because of my interaction from a state with a particle at momentum k to a state with a particle at momentum k minus q, k prime plus q, and a hole at k prime. Okay? So that's this matrix element. Just so that it doesn't seem very mysterious, if you wrote this out and just contracted the correct annihilation and creation operators, you'll find that this is just 1 over volume square mod VQ square, okay? Where I just use the formula of H int that we wrote down yesterday in momentum space and contract the correct indices on either side. So this is just a matrix element for the process that we described here, okay? So that's one piece. The second piece is in Fermi's golden rule, you require that there be energy conservation as well. So we've asked that there's momentum conservation. That was already enforced. But in Fermi's golden rule, the decay processes only happen not through virtual transitions, but through actually allowed transitions. So energy has to be conserved in the transition. And so we need that the starting energy is EK, which is the energy of Fermi surface plus particle. The final state energy is particle at K minus Q, particle K minus Q, particle at K prime plus Q, minus the whole at K prime. Everyone sees that this is the starting energy, final energy. The delta function in the Fermi's golden rule asks that this be exactly equal to 0. Okay? So those are the two pieces in the Fermi's golden rule. And now we're going to give a very simple argument just coming from this, that the lifetime, which I really erased, the lifetime is proportional to delta E to the minus 2. Okay, so clearly the only terms that are going to contribute to the formula in Fermi's golden rule must, as we said, because of the delta function, obey energy conservation. And 2, they should be consistent with the Pauli exclusion principle, because if it's not, the matrix element is 0 unless unless the k's and the k prime satisfy the picture that we drew up there. Okay, so just what these two in combination are already going to restrict the phase space of allowed scatterings a lot. So let's write it down, draw a picture. So energy conservation, like we said, was energy of a particle, initial state minus energy of the final state is equal to 0. And so just rearranging this, I find that Q minus EK prime, right? Okay, so let me draw a big picture here. So again, I start with a particle excitation at K prime. I'm looking at the process where it's scattered to a particle at K prime minus Q, while a hole is scattered from K to K minus Q, while a hole is scattered from K prime to K prime plus Q. Okay, so these are what all these momenta mean, and the energies are of these corresponding excitations. Okay, so this difference here is the energy of this particle hole excitation. Does everyone see that? It's the energy at K prime plus Q minus energy at K prime, energy at the K prime plus Q minus energy at K prime. This was a particle hole excitation because I excited a particle from inside to outside. So this energy always has to be greater than 0 because a particle hole excitation costs energy. Okay, great. So that means because these are equal, this has to be greater than 0. Okay, so what does that mean? What that's telling me is that the energy of my initial state with my particle just at K prime is bigger than E of K minus Q. or in other words, what it's saying is that for this particle to decay into another particle and a particle Hall pair, it has to lose energy. It has to give some of its energy to the particle Hall pair. So the only places that it can scatter to, which have lower energy than the starting state, lie within the shell of width delta E from the Fermi surface. Okay, does everyone see this? The original particle has energy delta E above the Fermi surface. In the process that we are looking at for decay, it loses energy because it creates a particle Hall pair. That means when it loses energy, it has to end up somewhere in a shell between here and the Fermi surface. Can't go into the Fermi surface because of Pauli exclusion. Okay? So that's statement one. This shell is the only allowed places it can end up in. Okay. Now let's think about this bit for the particle Hall excitation. So the maximum energy that can be gained by the particle Hall excitation comes from this particle just decaying right out to the Fermi surface, right? So we said that the width of the energy shell into which this particle can scatter into is delta E. So that tells you that the maximum energy it can give to this particle Hall pair is when this just goes straight down to the Fermi surface, and that's delta E. So this K prime then has to be within a shell delta E of the Fermi surface. Okay? Yes? No? So what have we done? What we've done is said that we've bounded the places where this K prime plus Q and K minus Q can be. K minus Q has to be within this outer shell of width delta E. K prime has to be within this inner shell of width delta E as well. Okay? Hall has a negative energy as compared to the Fermi surface, yeah. Right? So that's why I draw it within the Fermi surface. But the point being that the maximum amount of energy that it can get to excite out is given by delta E. That's the maximum amount of energy this particle can give it. And so then that means if it's anywhere deeper in the Fermi surface, by Pauli exclusion, it cannot scatter into another occupied state. So it has to be stuck to a shell delta E within the Fermi surface for there to be allowed states. Okay? So then this already allows us to just upper bound the decay rate up there without doing any complicated calculations. Yeah?
In some sense, we have an upper, like the particle state, in some sense, are bounded from above and the whole states are bounded from below.
That's right. That's right. So there's a huge restriction on phase space just because of these two. Pauli exclusion plus energy conservation tells you all the scattering of interest that's possible is happening very close to the Fermi surface. Yeah, that's the phase space available. And this is going to give us a lifetime, just this simple observation without doing any more complicated integrals. And let me just show you how. So in that formula up there was this matrix element, right? So which we said was proportional to this. So let's just to simplify our life, say that this is bounded above by the Q is equal 0 component. Right? So this was the case for both our, for the short range case we thought about yesterday, for screened Coulomb, for Yukawa, all this is true. Mostly we're not going to worry about the Q dependence of this matrix element. And so then we can say H bar of a tau K is less than we pull this out. There's the delta function of which Well, let me write it out. E minus Q. Okay, so then we do the usual trick of converting these two sums to integrals by pulling out the volume factors. Right, and then we have two integrals. One for, and then we use the density of states instead of the k-space measure to go to energy. And then we have two integrals in energies. One is over EQ, the other is over EK prime times this delta function, right? So we know that this delta function in along with where this matrix element is non-zero forces you to choose K prime and K minus Q within these two shells. So just right off the bat, without doing any other integrals, I could say that this is upper bounded when these two energies are within those two shells. So there's a factor of delta E squared coming from that. And then there are extra factors of density of states at the Fermi surface coming from these two terms when I approximate Q and K prime to lie within delta E of the Fermi surface. Right, so I'm not so concerned about these factors. What I want to emphasize is I've got this. And I've got this just because I have two integrals over energy and a delta function, and the two integrals over energy are both on shells of width delta E. Okay? So really, just without doing anything complicated, we've already seen that tau k then, even by being sloppy and taking upper bounds, is proportional to delta E to the minus 2. Okay, so it's a sanity check, and is this kind of calculation and the answer it gives you is the reason that you believe that Landau's Fermi liquid theory has any hope of describing the physics of the interacting system in the limit of really low energies. Okay? Yeah. Okay. I think I'll just stop it at that. I have a much. Yeah, I'll continue in the next class. Any questions about this?